down half of a half, and that's how things decrease exponentially. So let's set up our model. So I have my so A is some A0 e to the minus natural log of 2 times t over the half-life for this is 5,730 years. Okay. So I'm starting with some initial A0. A0 is the initial amount. And let's say that is equal to, 100% of something. It's 100%. Over time, this thing has decayed down. So now my A is now down to 0.15%. It's very, very small amount as this. Started with 100%, now it's 0.015%. Well, I can use all this now to find out the time. That's what I want to solve for, is the time. So over here, I can simply write my A0 is 100%, so I get 0.15% is 100% times e to the minus the natural log of 2 times t over 5,730. Okay, let's figure out the percentages right away. Simply divide both sides by 100. I get 0.0015 is equal to e to the minus natural log of 2 times t over 5,730. I just divided both sides by 100. Now what do? I need to get rid of this exponential, so I'm going to take the natural log of both sides. I'm solving an exponential equation like we did in the last section. I take the natural log of 0.0015 is equal to the natural log of, I'll put this over here, do a different color for what I'm doing. 0.0015 natural log of e to the minus natural log of 2 times t over 5730. So this is what it is, but this, it's the inverse function. So now this becomes, the left-hand side is the natural log of 0.0015 is equal to minus the natural log of 2 times t over 5,730. What am I trying to solve for? The time. How long it took to go from 100% down to 15%. So I simply solve for t. So t then is, get the negative sign there, I have minus 5,730 times the natural log of 0.0015 all over the natural log of 2. Okay, so I'll plug this into my calculator and get an approximation. I'll do the approximation in a second. Now, what I usually do is, you don't have to use the negative, but you can, because you know it's going to turn out to be positive. Let's plug it into our online calculator here, just so everyone can see what I'm doing. Turn it on, clear the screen, and then we just get, I'll use a change the sign, 5,730 natural log of 0.0015 divided by, and over here we have the natural log of 2, ln of 2. You get 53,752 years ago, approximately. So I'll put it approximate like that. So it's approximately 53,752. 53,752 years old. That's how you do it. So that's all that entails. So make sure the answers are correct. Trying to make sure everything's not messed up. We have so many things going on, so I have to keep it all in balance. Yep, exactly that. Okay, so we're okay there. Wasn't sure if people were asking questions because they didn't get the answer in the back and making sure the answer was correct. That's all it is. Okay, so let's move on. That was number 1. Let's take a look at number 3 now. You're going to determine which type of model are you working with. And then find all the parameters in that model, plug it in, and solve for the missing aspect that you want to determine. So take a look at number 3. Prozac has a half-life of 2 to 4 days. If a patient takes a 20 milligram pill, how long will it be before the amount is reduced to less than 0.1 milligrams remaining in the body? Okay, so let's put our model over here. So let's take, and we'll give it a range of values. Since the half-life is 2 to 4 days. So you could take an average of 3, or you could find the minimum half-life is 2 days and the maximum is 2. So you could get a range. There's many ways of analyzing this. So we could look at 2 aspects. We could look at a half-life of 2 days to get the quickest amount out of your system, and the largest is a half-life of 4 days. Now, if you want to be sure, you look at 4 days. That'll kind of make sure that you're down and it's at that level. Now, it starts out at, in this case, both cases, they start out at 20 milligrams, but we have a difference. We have A is equal to 20 milligrams times e to the minus natural log of 2 times t. T is now going to be in days, where the previous one time was in years because the half-life is in days. Over, here's the minimum, 2. And then you have the other one, A is equal to 20 milligrams, e to the minus natural log of 2 times t over half-life is 4. 2 different types of things. We want to find out, find t.
Professor, sorry to interrupt. I can't see just because you're still sharing the screen to the calculator.
Yeah, I'm still on the other thing. Yep. So over here, just I'm looking at half-life's 2 to 4 days. Half-life for 2 days, you get one thing, and half-life for 4 days, you get another. So the objective is find t when A is equal to 0.1 milligrams. Okay, so let's do both of them. We'll kind of work it out over here. So let's start with this one. So 0.1 milligrams is equal to 20 milligrams e to the minus natural log of 2 over 2 times t. So I need to solve this. Take logs, get rid of the units of milligrams. They cancel out. Take the natural log of this. Well, let's divide this first. 0.1 divided by, I'm going to divide everything by 20 to make it a little bit easier for us. So take 0.1 divided by 20. And just going through, you're solving a logarithmic equation now. 0.1 divided by 20 gives you 0.005. So this could be 0.005. Okay. And I'm going to take the natural log of that. This coefficient is going to be gone. I'm going to take the natural log of this. So what happens is this becomes natural log of 2 over 2 times time. By taking the natural log of an exponential, it just gives me the argument of the exponential. Then I can solve for t over here. So t then is equal to a minus 2 times the natural log of 0.005 over the natural log of 2. So if I plug that into my calculator, I'll just do this directly over here. So I end up with minus 2 natural log of 0.005 divided by the natural log of 2. And I get 15.28. So approximately 15 days, approximately. Now, if I use this instead, the only difference here, this 2 would turn into a 4. You kind of see that? So everything else would be the same. All the analysis is the same. And in the end, I'd have t is equal to minus 4, because everything else is consistent, natural log of 0.0005 over the natural log of 2. And it's just going to be twice that. So this would be about 30.57 days. So t is approximately 30.57 days, which is, again, approximately 31. This is 15 and a little over a quarter. That's 30 and a little over a half. So anywhere from 15 to 30 days. If you wanted to be sure that you were down to 0.1 milligrams, then you'd round up and you say, let's t equal to 31 days. And then I can be sure that I'm down to that level. Sometimes they give you ranges, and those ranges depend upon a lot of things, your metabolism and things of that nature. So, so if we want to be sure, then we can take 31 days or 30.6 days. So that's why you take the largest. But for certain people, they could reach it in half that time. But if you want to be sure, take the largest amount. Okay, so that's problem number 3. And someone's had to look at number 4 over here. See, Aimovig has a half-life of 28 days. If a patient takes a 140 milligram dose, how much will be in the body after 100 days? It's a little bit different. So Aimovig has a half-life of 28 days. So let's set up our model. A is A0, e to the minus natural log of 2t over, in this case, 28. T is going to be measured in days now. Now, this is a little bit different. They're not telling us the time. They're telling us the initial amount and then the time to give us the final amount. So now, in this case, when, after 100 days, so in that case, that's t equal to 100. And the starting initial amount, A0, is 100 milligrams. How much is remaining? So the amount remaining is 100 milligrams, e to the minus natural log of 2 times t now is 100 over 28. So then I just plug everything in to my calculator and get my answer in terms of milligrams. 100 e to the minus the natural log of 2 times.
Excuse me, Professor. It's 140 milligrams.
Oh, 140 initial? Yeah, 140. So I'll put it as 140. Let's go back. Make it 140, and then that times 100 days divided by 28. Oh. And I get a total of A approximately equal to 11.8 milligrams. So approximately that much. I think if that's correct. Make sure I got everything correct there. Yep, 11.8 milligrams. Just plug everything in. That's all it is. Everyone kind of see what I'm doing now? Here I didn't need to solve for the time. I was given the time. Here I was given the final amount and they needed the time. That's the difference in the types of problems that are there. Okay, number 5. Number 5 over here. The world population at the start of 2020 was approximately 7.8 billion people. if the population was to grow net growth rate of, or births minus death percentage at a rate of 3.5% per year, what will be the population in 2040? We don't grow that fast, luckily, because if we did, there would be a problem. But here's our population model. P is initial population, E to the RT, where R is the growth rate as a decimal. It's the growth percentage written as a decimal. Growth percentage written as a decimal. Okay, so in 2020, there was a total of roughly 7.8 billion people in the world. Now we want to go into the future. We want to find out in 2040, how many people are there. So what do we do? We're advancing 20 years into the future. So I take my 2040, subtract the 2020, and that gives me 20 years. That's how much I'm going into the future, 20 years. So T, 20 years from now. I don't put in 2040 up here because it's the years from 2020 that I'm looking at. So set up my model. P is 7.8 billion. If I put in billion, my answer is going to come out in billions. E, the growth rate is 3.5%, but I want to write that as a decimal, so 0.035. In all these formulations, it's always the decimal equivalent of that percentage. So it's equal to 0.035 times and 20 years into the future. So that's what I'm looking for, computing that. So doing this, I use 7.8 times my E to the 0.035, that's 3.5%, growing for a total of 20 years, 2020 to 2040. And in that case, the population would be 15.7, and our answer is billion. Luckily, we don't grow at that rate. The world grows at a little over 1%, and we have to shrink that down because that would be, it's a tremendous growth rate. But luckily, that's not the case. But that's why some people are concerned about populations growing too rapidly, because it could cause problems with resources not being available.
Excuse me, Professor, I have a question about number 5. I'm not getting that answer in my calculator. I'm not sure what I'm doing wrong. But what is it that you're typing in?
I'll just show you on the calculator here. Same thing. I put it into mine and just got that out. So turn it on, clear off the last problem. So I take my 7.8. And I'm going to use my second function. Now, make sure if yours doesn't do this, I'll show you what you should do. And I have my 0.035 times 20. I get 15.7. Now, some people may have calculators that are not as sophisticated as this one right here. I have another one. Let's see. Maybe I'll use this one. Here's another more simpler calculator right here. And let's try the same thing. So on this one, put it on 7.8. And I do my second function, and I'm looking at my exponential, and it automatically puts the parentheses. So 0.035 times 20. And I get the same 15.7. So either way, you should be getting that.
Okay, I know what I pressed wrong. Okay, thank you.
So either one way, you should get that answer. I did it on 2 different calculators to see you get the same exact result. Okay, then let's take a look at another problem, number 7. You can see some interesting problems in biology and other stuff that comes from a very simple model and gives you useful information. Here's Streptococcus lactis bacteria, double in amount every 48 minutes. So strep, it doubles in 48 minutes. Okay. If you become infected with only one, so you have one, you start with one, of those bacteria. So you have one bacteria. How many will you have in 3 hours? So how many in 3 hours? Now this is similar to, but this is doubling. So it's different than this. There's another exponential growth where you could have, the amount present or even population, if you use that, is the initial amount times, you could then use, instead of 2, since it doubles every 48 minutes, it's 2 to that power. So it's 2 to the time in minutes over 48. Kind of like a half-life thing, but it's doubling. This is one thing. Sometimes I use, that's the more accurate one, but let's see, did I kind of use, sometimes I use different ones over here. Guess we can take either one. Let me just see which one we have over here. So let's take this bottle. Because we could take the E and do that as well if we wanted to. Okay, so that one, I should throw in an example on that one because it's a little bit different. I had an example of something similar. For the E. coli bacteria, we have that one. We have something similar where we could do that. So we could either do it this way, or we could actually approximate that in a similar fashion using this same one. So that's what we're doing. This is another way of doing it. You get the same sort of answer. But let's go back to the example I have in the textbook, which we're going to model that. So in this case, we know our P0 is 1, and we want to find P. But we got to find the R value. That's from this information of its doubling in so many minutes. So our model looks like this. P is 1 bacteria, E to the RT, where T is time in minutes. So T equals the time in minutes. See here, 3 hours is 180 minutes. So 3 hours is equal to 180 minutes. So that's what we're going to be looking for. But now R is what we have to figure out. So what we have is this. This is a function now of time. So we have P of T is equal to E to the RT. What we know, when I end up putting T equal to 48 minutes, okay, then I can start with some initial P there. It doubles the amount. After 48 minutes, this gives me my amount that's, if I set it up with P0 initially, I could do it as P0. We're going to do it 1 in a minute. Let's just get the R value. So after 48 minutes, that amount doubles. So I now have 2 P0. And that's equal to P0 E to the R is what I'm looking for. T is what I've been given. I've been given 48 minutes for T times R. The P0s go out. Then I simply take the natural log of both sides. I have the natural log of 2 is equal to 48 times R. Now I simply divide both sides by 48, and I get my R is the natural log of 2 over 48. That's what goes into my model here. So now I plug in everything and I'm ready to go. I could have done it with the 2, the doubling time as well, but you get the same answer. Very good approximation to it. So this is my model. The amount of bacteria, the population of bacteria present is starting out with 1. I have my model, it grows and doubles every 48 minutes. So my R is equal to the natural log of 2 divided by 48 times my time. Now I'm saying after 3 hours, how much is there? So P after 3 hours, T equal to 180 minutes. Make sure you don't mix the units, they have to be the same. So I get e to the natural log of 2, 48 times 180. And plugging that into my calculator, let's see what I get over here. So starting out with 1 and 3 hours later, second function, natural log of 2 times 180 over 48. And in this case, you'll have 13 in that time period. So it should be in that time period. It has a typo there. There's got to be a typo there. Natural log of 2. So what I have over there. Yeah, so there's a typo in there. I got to correct that. So in this case, what I get over here, T at 180 minutes gives me approximately equal to, and we can't have a fraction of it, so there's just 13 of them, 13 bacteria. So it starts increasing, and then you'll see it double again. If you went to 6 hours, it wouldn't double. It would actually go up much more than that. If you plugged in here 360 for 6 hours, you see it would grow up at a much, let's just do that. 6 hours. So now I'm to 360 minutes. Just so you can kind of see what would happen there. Doing the same sort of thing. So I have my E, a natural log of 2 times 360 divided by 48. Now that goes up to 181. So it jumps from there up to about 181 bacteria. Double the time, much more than double the amount. It went more than 10 times the amount in that time. That's the problem with exponential growth. It gets going and it just keeps plowing through. And that's the problem with the spread of COVID. It spreads exponentially. Now, we do have things to curve it down and flatten the curve as I speak. But if it was left to grow uninhibited, it would kind of be crazy. Okay, so we have one last problem from these sets. And this is number 8. And it's the same sort of thing. Now it's doubling every 28 minutes, so it's the same sort of thing. So our model is going to be the same. P of T is my P0 e to the natural log of 2, but instead of 48, this is a different one. This is Staphylococcus aureus bacteria every 28 minutes. That's the model. Very similar. So this is doubling 48. Go through the same analysis. It would double every 28 minutes. You want to find out the following. So again, let's assume that you start out with 1 bacteria. How many will there be in 5 hours? So let's say P0 is just 1. Usually you get more than 1 when the initial infection, but we'll just assume that. And we want to do 5 hours, so that's equal to 300 minutes, 300 minutes. Because I have to, this is in minutes, so everything has to be in minutes. So I plug everything in. So P after 300 minutes, the population would be my initial amount, is that, times E natural log of 2 over 28 times 300. And just plug everything in and see what we get. The second function, E natural log of 2 times 300 divided by 28. In that case, we have 1,680.
Excuse me, Professor, it wouldn't be 10 because it says in the problem if you were infected with 10.
Oh, did I say 10? I can't read it over here. Oh, 10, yep. I didn't see that. So it's going to be 10 times that, so I add another 0. So 16,800. So P0 is 10. This just multiplies it, so it's just going to add that. So that's how many there would be. So you can see where it really grows dramatically. And it's really, that's just in 5 hours. You know, overnight, you can see why these bacterial things do kind of overtake our bodies. Now the body's then starting to fight this, but it's fighting kind of an uphill battle with something that really wants to grow at that rate. And that's all it is. So again, this is populations of anything, you know, P equals P0 e to the RT. And you have to find that R if it's not given to you. Now, if you're given, R is a percent growth rate, or you can figure it out by getting the doubling time or the quadrupling time, anytime, the tripling time, anything like that will allow you to find R. If you're given T and you say triple, then this would be the natural log of 3. If it triples in that time. That's all it is. It will work out to be whatever that is over there. Okay, so those are all some basic models using exponentials, and we didn't do the logarithms, but logarithms are usually oftentimes come up with scales, logarithmic scales, because they enable you to take really large numbers and compact them down. You're really looking at their exponents, and that's what makes it easier to handle in that regard. So the test on Monday is on chapters 8 and 9. Chapter 8, which is the analytic trig. So we covered a number of different things in that section. Let me just kind of go through what we covered. So you had all your triangles, your solving triangles. We went through that. In addition, we looked at trig identities. We used Euler's relation, but we didn't really calculate with it. We just used it to find some of the trig identities. So here, trig identities, and kind of using those. We use those in analyzing things all the time. And then solving trig equations. And then finally some, applications of the triangles, applications of trig. Functions. Mainly we're just dealing with, geometric ones. We're not looking at cyclical ones. It can also apply it to its problems in electricity, AC electricity movement. We didn't. We just limited to that. There are many more applications for trig functions. And then in chapter 9, that was analytic exponentiation. And by exponentiation, we also include logarithms. So some of the first things we were asked to do is look at the various properties of logs and exponentials, how to rewrite them either in a compact form or expanded form. So we looked at the properties of the exponentials, as well as the properties of logarithms. All those rules of exponents and rules of logarithms. And then we looked at solving exponential or logarithmic equations. Solving equations involving them. How do we deal with an exponential equation or a log equation? We use the inverse function quite often. And then what we just covered now, some applications. Not an exhaustive list of some applications of, exponentials and logs. So here, the solving the triangles over here, that's our right triangle trigonometry. That also involves the oblique triangles, law of sines, law of cosines, trig identities, showing that two expressions are the same, or expanding a single trig function using trig identity. So there's two types of problems that we did over here. So you can kind of drill that down. But this is what our test is on. These two chapters. How do I use analysis with trig functions to solve problems? And how do I use analysis with exponentials and logarithms to solve problems? So chapter 8 practice test covers this. Chapter 9 practice test covers that. Your test will be a combination of the two. Now, there were other things that we did. We did Euler's identity, but that we just used as a tool. Now, that's a very important thing, but that's why I wanted to at least show it to you. E to the I theta, cosine theta plus I sine theta. That's something, if you go on in mathematics or engineering or something, you will remember that. That is something that will be a common tool that we use. And we use that to derive some of the trig identities, which we then use to transform one trig expression into another. Double angle formulas, half angle formulas, and a variety of things. Kevin, have a question? Or?
Yeah, and you said you're gonna give us the formulas, right?
Formula, you have that, if you want, you can take your formula sheet, if you will, because I have that at the back of the book. I think I have one, right? I'll put one online here, and I'll let you print that off. Because if you look at the textbook, at the very back of the textbook, there is a list of those formulas. I'll just take a look at that. I'll give you the page number here. On page 449, trig identities and relations, 449 and 450.
Okay, so you'll allow us to take that with us?
Yeah,
Well,
use that. You can use that.
Okay.
Yeah, that's got much more than you will need. Now, over time, you want to try and learn as much as you can with those, because it does take time to look stuff up. So the things that you use a lot, you will commit to. And that's why I'm not so afraid of it. But don't just say, oh, I'm not going to memorize anything, because that'll slow you down in working problems. Where you want to use it is, oh, I forget, is that a, plus or minus here? So you have to quickly look it up. You need to be comfortable and say, I know a general form of that. And how do I do it? So you can use that. You can just, take a picture of that or something like that and have that. Or I might, I probably could make that. I'll see. I probably could make that available on the test. I'll see. But either way, you can have that out as a backup to have it available. You will be able to use that. So it's kind of laid out. We've covered everything. We worked lots of problems. Pretty much all the problems in the textbook almost. So you should have a reasonable idea. So it's just these two chapters. Any questions? Now on Monday, the test is scheduled to start at 12:30. I think there was somebody that wanted to start early or something like that, if I'm not mistaken. Because I can open it. I'll open it to start at noon. Just in case someone has something after at 12 noon. Unless someone wants it even earlier than that or not. Okay. Any questions? Any questions here? Okay, so everyone's Finish another week. Stay safe, stay healthy, smile, wake up. We will be back. I won't see you on Monday. You'll just go right into responders and then, to Blackboard, then out of the responders into Blackboard again without responders to upload your work. And that's when I'll look at all the work to cover this. The test will be 100 minutes in length, so it'll give you some time to kind of work through that. Really, it's going to be 75 minutes, but I'll let it go for 100 minutes. It's something you should be able to do in an hour and